Hey, everybody. Um, Today I'm going to, this one is going to be about the junior labs for a student who are going to attend the lab for this coming semester, start on the 2nd of August, uh, 2021. I take a look at the EL313. Uh, it's about the transistor or biasing transistor. And I mentioned about how transistor work as the electrical switch, transistor in the term of a switch. This one we will go through the biasing transistor, and also I will focus on our NPN transistor, and you should be able to continue with our PNP transistor. And actually this one I mentioned earlier, hold on a second, is there we'll focus on our NPN transistor and refer to what I talk about the basic relations in the term of current in different point, as well as the voltage at different point. I mean for collector, for the base, and emitter. Okay, as the lab's supposed to be working on the hardware. In the term of you need equipments. Of course, you need their power supply, and you need oscilloscopes, and of course, electronic components. Look at the circuit. You don't have so many components. You simply have two resistors, one transistor. At this point, I used 2N2222, and we'll go through piece by simulation to demonstrate how to work on the lab. So it's your job to learn how to use their DC power supply and their oscilloscope, especially for the reading, because you need to put down the number. This is the table that you need to put down the number. In here, you have what? We have our VRC. This means you need to find the voltage drop across the collector resistor. You're looking for IC, the current flowing through RC. You have VRE, or the voltage drop across the emitter resistor. You have look for IE, the current flowing through RE. And finally, you're going to calculate for alpha, which is equal to IC over IE. Something missing here. Okay, let's take a look quick. Nope, I probably missing at the bottom line here. Doesn't matter. Okay, look back at the basic relations. As you know, that your IC that's equal to beta IB, where beta is the common emitter current gain, and IE equal to IC plus IB, and you can look for alpha, which is equal to beta over beta plus 1, where in this case, in the circuit down here, we are looking for alpha, or the common base current gain. Okay, let's get started with the circuit. It looks simple, but when you work in the lab, you need to work on the DC power supply and also oscilloscope for the reading. But in the lab, you connect a circuit like this. You supply the voltage of plus 12 volt through the collector. You have RC equal to 1k ohms, you have RE equal to 1k ohms, and you need to adjust VEE until you achieve VRC, or voltage drop across the collector resistor, to be 1 volt, 1.5 to 8 volt. So you need to put your oscilloscope across the RC and measure VRC until you get the VRC to be 1 to 8 with the increment of 0.5 volt. Okay, 1.5 to 2.5. And after that, you measure IC, VRE, RE alpha. Okay, hopefully this is very simple, but when you work in the lab, it's going to take longer. And we have more circuits to work on. But this one is just for you to get started. Okay, now it might look different because I'm going to use the PSpice to work on the lab. Actually, I already draw the circuit, but we can work together again. So let's disable the circuit. Before the way I connect the circuit again, I just tell you the name of each part. For this one, the supply voltage, you control G, right? Get new part, and that's the VDC. Okay, that is. So I'll close. Ignore this. R is R, and transistor is you type Q2N, 222, Q2N. Okay, this is going to pop up. And for ground, that's going to be your AG and D. Close it. And what else? For R, remember again, you type R, you place, left click to place, right click to stop. You want to rotate, you simply control R. That stands for rotate. Okay, I undo it. Now this is the common based circuit. As you can see, what we call our common base. Well, your bases are short to ground. That's why we call our common base. And you have a very supply voltage V3 at this point. And I also to take the number down on the table, I also label, this one as VC, the collector voltage. You simply you double click on the line. Oops, what happened? You double click, okay, and you type in VC. Same as for this one as V in, and also I need a VE, and I also need a VB, but you already know that VB is 0. And you double click on the supply voltage. Something wrong with my mouse, so I just go to attribute, edit attribute. You can simply type in 12 volt. That's going to be your supply voltage, 12 volt. So from the table, so how are you going to take down the number? We are looking for RC, VRC, or voltage drop across RC to be 1 volt. And you have a supply voltage right here is 12 volts. So what you need to do, you need to vary VEE, and then you plot looking for VRC equal to 1 volt, 1.5 volt, 2 volt. Okay, so what do you need to do? You need to go to analysis, you need to go to setup, okay, and then you want to vary your V3. So you select this is sweep, and the voltage source is your V3, and I start from 0, end up to 10, and increment is 0.5. Sorry. All right. So the plan is to plot between B3 on the x-axis and the voltage drop across the 1k ohms or your RC. Actually, I can change this one. Somehow my mouse is not very good. So this one, I'll put this one as there to be clear. So that's one RC, and my R2, that's going to be what? E, right? The emitter resistor. Okay, so again, you go to setup, you go to this is sweep, and you start from 0 until 10. Increment is the 0.5. So your V3 going to start from 0, 0.5, 1, 1.5, and so on. Now you can do your simulation. You go to analysis, you go to simulate, and your plot will pop up. So the x-axis is the V3. So you start from 0 and you end up with 10 volts. Now you go to address. You're looking for the voltage drop sorry, across the RC or 1k ohms. So you need to type expressions for to look for VRC. So you have a 12 volt minus the VC. That's the reason why I label this one as the VC, collector voltage. So you go back to your plot, you put 12 minus, and you look for VC. Where's my VC? Here. Okay, so you do okay. You have the plot. Let me change the width. Okay, to be easy to take a look. Now you pick up your cursor, and for the y-axis, this is the voltage drop across the collector resistor, right? And this is the xy coordinate. This one, the first column is the V3. The second column is the voltage drop across the collector resistor. So you can click for the case that you want VRC to be 1. So you simply move down. You take a look at this number here until you get closest to 1. I got 0.99, and it jumped to 1.0053. You can take either number. So I'll take this one, 0.9975, and that's come from V3 equal to 1.6452. Okay. So in that case, you can do either way. You can also add trace. You look at this one, V3 equal to 1.64, and you can go to plot, and you go to add plot to window, and then you add trace, and you want VC. Actually, you want looking for wait a minute, hold on a second. So you look for IC, right? For VRC equal to 1 volt, you look for IC. So you go to your plot. This is your IRC. You click OK, and you move up to, let's see here. Okay, you need to click on this one, so that would change. On the x-axis, you look for 1.64, right? So you need to move this one a little bit. It's still at the, sorry. Actually, I want to look for IRC. Let's get to, okay, I have IC equal to 0.997. Maybe I move this one a little bit. Okay, and then you can take down the number that's become your IRC, and you put down the number right here, 0.997, and you can look for voltage drop across the collector resistor to be 2 and then to 5. This is just for example. Or to be easier, and back to your plot. Okay, I go to this plot, and you want your, oops, you want your VRC closest to 1. Okay, I have 0.9998, or UV3 is that 1.6479. So you just go to UV3. You go to edit, you go to attribute, and then you put our 1.649, if I'm not wrong. Let's get back to the plot again. 1.6475, that's in volt. 1.6475, your save attribute, you click OK. So this is your V3 that result in the voltage drop across the collector resistor of 1 volt. You go to analysis, you do simulation. Okay, it's done because this one is show current, it's show no error. You go to analysis, you go to display result and schematic, you enable it. See, this is your VCC 12 volt, and you have VC equal to 11 volt. So the voltage drop across the RC is going to be 1 volt. Okay, 1 volt missing. And you also know VE, this is your V in, or V3, that's 1.6475. So you can take down the number VC and VE into your table. Okay, just let's see. And this one you can see your VRE. This is your voltage drop across the collector, right? You're looking for 1 volt, and your VRE right here, your VRE. Actually, that's supposed to be VC. Or if you look for the voltage drop across the emitter resistor, you simply subtract negative 1.648 by negative 642.31 millivolt. Okay, you're done with your voltage. And now look for the current. So you enable current display. For AC, you can see at this point, this is your AC, right? To be your 0.999. Maybe the number a little bit different. And what is your RE? This is your RE. 1.005. I got 1.003. So it's about that number. Maybe we missed the V3. Okay. So you have IE, and you can find your alpha is the ratio of IC divided by the ratio of IC and IE. So simply you divide 0.997 by what 1.003. So it's less than 1 for your alpha. That's the become common base current gain. Okay, so that's about it to work through your circuit. Just simply using a PSpace, but it's going to be take more time when you work on the hardware. Now something to add up. Since we already have the final simulation, you look at this one. I'll take a look at that. For VE equal to 5.71. I redraw the circuit, and you will see end up to be 7. So it's about 7. So VRC or voltage drop across the collector resistor is about 5 volt. That's what you're looking for. And I also wrote down VE, VC, IC, IE. Now let's apply the basic equations or basic expressions, relations. You know that the VBE at this point, you notice, equal to VB minus VE, and end up with 685.74 millivolt. So this is become the forward bias between the base and emitter, and you need at least 0.7 volt, right? That's what we'll be been talking about. But for this one, VCE is greater or equal to 685.74 millivolt. That's going to be your active mode. Okay, so and that means your transistor is going to be on, right, or in the active mode. So does that make sense? Now for IE, since you already know that your VE is what, negative 685.74 millivolt, and your V3 is what, negative 5.71 volt. you can find your emitter current. Simply subtract, or find the voltage difference across the emitter resistor. Just give you a 5.024, same as that we got from our P-space. And if B is known, then IB equal to ICO beta, or IB equal to IE divided by 1 plus beta. But in this case, since you already look for alpha, you can also find the relation between alpha and beta from that. Okay, so that's all about the lab, and we will continue more circuit. Actually, the next one is going to be your common emitter circuit. Okay.